Cool. Thank you for the awesome intro. Hi, everyone. I'm Soroush. If you know me, you might know me from my blog. I write a lot about programming there. I used to write about how I don't like Swift and I wouldn't write Swift, and now every post is about Swift. So that's pretty good. I even do server Swift stuff, which is great. You might also know me from the podcast I do with Chris Zombak. This is a pretty boring landing page. We should probably do something about that, Chris, if you're watching. You know, 6 months from now when you're watching this, we should spruce up this page. So today we're going to be doing a little live coding. Show of hands, does anybody not know what Sudoku is? All right, I think everybody knows. All right, we got one over there. Cool. So for you, basically, this is Sudoku board. The rules are pretty simple. You fill in the empty boxes with the numbers 1 through 9. And every row, every column, and every one of those little mini grids has to have the numbers 1 through 9 once and exactly once. And so these are fun to do when you're like on airplanes and you're really bored. But I thought it would be really fun to use some cool Swift features to write a solver for every Sudoku board. So we're basically going to take a crack at this. Our representation of our Sudoku board is like this, and we're going to build a better representation. So I'm going to run you through the stuff I already have set up, and then we're going to get to writing the sort of solver code. So the first thing that everything is built on top of, the core modeling component of this is the cell. Fundamentally, a cell can be one of many values. Initially, this is going to be like the numbers 1 through 9. If the cell is sort of what we call settled, which means we know what the value is, it's going to have exactly one value in it. But at any point, it might have, let's say, 5 values in it because of the position of the cell on the grid telling us which values it can and can't have. And so we build everything on top of this cell. A couple quick helpers here. Equality ends up being useful. A description, which, if it's settled, will print the number value of the cell. And if it's not settled, it will just print an underbar. And then we have 2 kind of convenience initializers here. One will just create a new settled cell. So you pass it one integer, and it will sort of create a cell from that. And then the other one is a cell that can represent any number. So sort of this range here, 1 through 9 inclusive, it can represent anything. So from this cell, we build our board. The board is basically an array of cells is a row, and then an array of rows is the board. There's a couple boring things here. We got to be able to initialize it from that ugly board string earlier. And I won't go through this code line by line, but basically, if the character is a dot, it'll return cell.anything. And if it's a valid integer, it will create a settled cell at that location. And if not, I'm not going to deal with sort of malformed input, so I'll just totally crash the app. Seems fine. And we have a couple helpers that we need here as well. So we want to be able to get every single cell, so we don't have them in that sort of array of arrays representation. So we flatten the rows, and that's how we get our cells. The board can print itself as well, and you'll see that representation here. It's kind of a nice little representation of a Sudoku board. We also want to know if the board is solved. And so the way that we do that is basically using this little function called all, which returns true if every element returns true for this test. So basically, if all the cells are settled, the board is solved. These next 3 are important. Basically, given an index, so your board is a square, and it has the numbers 0 through 80 as its indices. And given any one of those indexes, you want to be able to access the row, you want to be able to access the column, and you want to be able to access the mini grid for that given index so you can check stuff. And we use that in these last 2 functions here. One is can update. So basically, given a number, can I update this index to that value? And it basically checks that the row, the column, and the mini grid, it checks that none of them have that value. And the last thing that we have is this update function, which will update the values for a given cell. If you update to an array of values, then it'll just set that down here by figuring out the row index and the column index. But if you set it to exactly one value, it will make sure that it can update that, because if it is invalid, then it'll have to throw a consistency error, basically. And so that consistency error is here. It's pretty boring. Doesn't really do anything. But it serves as a signal to other parts of the program that something went wrong. That is pretty much everything we need to take a crack at writing the solver. So we're in a playground, live coding environment. I think I've sacrificed the right animals to the demo gods. See how this goes. Shout out if I make a mistake, if I leave out there's no semicolons, but whatever you can do wrong in Swift, shout out if I make a mistake. So basically we have, we print our board beforehand, and we print our board after, just to see the before and the after. And we check is solved is false, and then we call the solve function, and is solved is still false. And that's because we haven't written our solve function. So that's what we're going to do right now. When I solve Sudoku puzzles, I thought the way that I do it is I just kind of run through all the cells, find a cell, and then check the row, the column, the mini-grid, and check to see if there's only one possible value that can go there. And if that's the case, I update that to that value, and then try to do the same thing over and over again until the board is solved. It turns out that this can't solve every single puzzle, but it's a really good place to start. So we're going to start by writing that solution. So we're basically going to loop infinitely while the board isn't solved. And what we want to do is we basically want to go through every single cell in the board. And for all those cells, we basically want to find one that's not settled. So if the cell is settled, we kind of don't care about it. Board.cells. You guys are letting me down already. Come on. Cells. Where's that S? There it is. Sweet. Hey. So if the cell is already settled, we don't care about this one, and we kind of just want to continue, go to the next cell, and find me one that isn't settled. For the ones that aren't settled, we basically want to run through the numbers 1 through 9, and we want to see if which of those numbers which of those numbers the board can update that cell to in like a valid way. So we have that handy function from earlier, so we'll just check if the board can update to the value, and that value is going to represent whichever 1 through 9 we're iterating through. But immediately we have a problem. We don't have the index that we need. And so the sort of easiest way to get at this is the enumerated function, and what that does is it returns us an offset and a cell. And so we have that offset, we have access to that offset. Now, if you are a reader of the blog, I have like a whole detailed post about why enumerated isn't exactly the right thing to use in this situation. So I've written a little helper here called with indices. Enumerated returns to you a number that starts from 0 and increases by 1 every time. For arrays, that happens to correspond to the index, but for other types of collections, that isn't always going to be the index. So if you had an array slice, and you sort of call enumerated on that, the first element of that is going to have an offset of 0, even though its index will be, let's say, 2, which is wherever that sort of array slice starts. It's not exactly right, so we have this quick little thing that will give us the cells and their indices. It's a little bit technically more correct. It's pretty pedantic, but I'm gonna go with it anyway. So we're going to use with indices, and that will give us an index instead of an offset, which is great. And so now we have a value that we can update to. So once we filter through this range 1 through 9, what we're left with is essentially all of the possible values that cell and at that index can be updated to. So we have this possible values array. From that, we want to do a quick sanity check. If the possible values is empty, then something's already gone really wrong, and this technique can't solve this board. So we're just going to bail out, and that bails out of the whole function. And the last thing we want to do is just update the board to those values that we found were valid for that index. So we have the index, and we have the possible values that it can be updated to. Now, there's a chance that this possible values has 1 item in it, and if that's the case, it will update that cell to an array with 1 item. And if that happens, then that cell is considered to be settled. And when we go through this loop again, it will contribute to basically the board being solved. And the last thing we need here, this is actually a throwing function, but in this particular case, it throws that consistency error. In this particular case, I don't care about the error, so I'm just going to discard it. Not a big deal. We will use it later, though. So when we run this, it's going to crash. Love it. I think it just needs to reset itself. There we go. So this solves our board. That's all we needed to solve the board. Yeah, there you go. So it turns out, as I mentioned earlier, this technique doesn't solve every board. So if we wanted to find a somewhat harder board, we can pull one of those up. And if I actually let this run, it will go into an infinite loop. So I'm going to actually put a quick condition in to make sure that doesn't happen. what essentially ends up happening is with an impossible board, it doesn't update something every value, and so it just keeps trying to find something to update and not finding anything. So we'll make a quick sentinel here that's just like, I don't know, settled something this iteration. We'll say that's false. And if our possible values does have exactly one element in it, that means we did settle something. So we'll say settled something this iteration equals true. And if not settled something this iteration, if we didn't find something, just return, because this technique fails at this particular board. So when we run this, we have, come on, love playgrounds. They're great. Cool. So we have our first puzzle, which solves correctly. And we have our second puzzle, which unfortunately doesn't solve. So we see here is solved is still false. And when I was solving this, when I was like trying to figure out how to solve this problem the first time, I was like, that's kind of weird. I kind of thought all Sudoku puzzles could be solved this way. And I did a little more research, and there is a blog post by Peter Norvig where he goes into a little more detail here and explains it in kind of a nice way. He says there are more sophisticated strategies. For example, the naked twin strategies looks for two, let's say, cells in the same mini-grid that both have the same possible values. You know that if those two values are going to go in those two spots, it's not going to be anywhere else in that, let's say, mini-grid. And so you can eliminate it from there and then continue on. And writing all these strategies could work, but it'd be like, there's a ton of different strategies. I don't want to code them all. I just want to code one that will solve everything. That's what I really want here. And so the way we're going to do that is instead of kind of using this naive solver, we are going to write a brute forcer. Or just brute force. So we'll update this so I don't forget to update it later. And all right. So the strategy here is basically, if we were to go through, let's say a given Sudoku board only has, I don't know, 60 unset cells. Each of those 60 cells could have one of 9 possible values. It's like 9 to the 60th. It's like a huge state space. And if we wanted to search all of that, it would take, I don't know, hundreds of billions of years. And I only have like, I don't know, 11 minutes. So I don't think that's going to work. But fortunately, we already have narrowed that space down because we've already checked which values are possible using this sort of naive solver. And we've already updated each of those cells to, let's say, one cell might be 4, 5, and 7. So it's not 1 through 9. It's just this limited range that we have to check. So that actually narrows our space down a lot. So the first step in brute forcing is actually going to be to call the naive solver and fill in the cells with all the values of what they could possibly be. And cool. So the essential strategy here is pick a cell that's unsettled. And you know what possible values you can have. So just pick the first one of those values, stick it in there, and try to solve that board. See if that board is solvable. If it is, then great. That was the correct choice. And if not, that was incorrect. And like proof by contradiction, you can throw that out and try the second possible value for that cell. And so on until you end up with a board that's solved. We're basically going to try every possible value with a couple optimizations that we're going to throw in later. So to do that, we essentially need, well, first we're going to check if the puzzle is solved by the sort of naive method. If that's the case, we can just return. And then once we've done that, then we basically need to find the first cell. So we'll check our cells for the first value that isn't settled. So not settled. Great. This must be so riveting to watch. And we actually know that that we're definitely going to get a value here. Optional is never going to be nil because we know that the board isn't solved, so we must have some cell that's not settled. That being said, you could use a bang, but I'm going to play it safe here and just use like a regular unwrap, or a regular unwrap and kind of return in the case that the value is null, which should never happen, but. Cool, so now all we got to do is we got to call board.update. And, oh, that's not right. We're not going to do that next. We got to check all the possible values that this cell could be because it's not settled as more than one possible value. So we're going to grab all the values in the cell, so cell.values. And for each of those values, we are going to we want to create basically a playground, a scratch pad that we can use to test if our theory is right that this value here is the correct value for this spot. And for people who've been paying very close attention, you'll note that our board and our cell here are both structs. And so with a struct, if you want to make a copy, it's as simple as just creating a new reference to the thing. So if we just write var copy equals board, this goes ahead and creates a full deep copy of that entire board. And we can go ahead and mutate that copy any way that we want, and it won't affect the original board, which is really great. It's exactly what we want. So once we have that copy, we can try to update the copy. We have our update method. Again, we need an index, and we don't have one. And we know what value we want to update to because it's the one that we're checking there. Let's go ahead and get that index that we want. So with indices, and then here we'll do the destructure of the tuple, and we'll do the unwrapping of the optional. And we'll have an index as well. And this needs to be .1 because it's now a tuple. Cool. Great, so now we've updated the value. This is a throwing function, so we need to wrap it and catch our error, which is possible. The error is going to be that consistency error. So we're going to say if that error is a consistency error, then go ahead and continue. That means that we thought we could update the spot at this index to this value, but it turns out that actually causes a consistency error. We were wrong. This solution is bunk. Throw it out and go to the next one. And when we call continue, go back to the top of the for loop, and the board that we copied is just gone. It's just dust in the wind, which is nice, which is exactly what we want. And then, so now we have a new board, and we have a cell that we've updated to something that we think might be right, and we need to solve the rest of the board. There's still a bunch of blank spots on the board. And to do that, the best way to do it is just to run the exact same thing again and see if you generate any consistency errors. So we're going to use recursion, and we're just going to create a new solver. And for the board, we're going to pass the copy, and the copy is the one where we've updated that one value. And once we have the copy, we can call brute force on it. And if that new solver is solved, then at that point, we can decide to copy the solver's board back to our own board. And we can take credit for the other solver's work, and we can say, actually, we did that. And copy that board back, and then return out of the function because we've got now a completely solved board. So this is basically all you need for the brute forcing solution. I'm going to go ahead and add a print here, which will show you the work of the algorithm as it goes through, which I think looks really cool. And let's see if this works. Run. Compiling, running. All right, great. So you can see it's kind of working its way through solving this problem. And as you'll note, it's kind of setting the values from the very beginning and trying all these different values. And that makes sense because in our solver, we said, just give me the first value that's unsettled. So it starts from the top of the array. There's a slight optimization that we can do here. And while this takes its incredibly long time to execute, I'm going to tell you about the optimization. So essentially, what you're doing is you've got a big tree. At the top, at the root of the tree, you have the first choice that you make. And that first choice has some number of potential options, which each represent a branch. And then each of those branches, that represents the next choice that you're going to make of which cell you should use. And that has its branches and all the way down. And at the leaves, at the very bottom of this tree, you have all solved boards. Oh, this is solved, which is great. Cool, we're not done yet. We have a small, awesome thing that we're going to do for the very end. So you've got this big tree, and all the bottom things are basically solved boards. But when you are going through this tree, sometimes you update a value to something and you get a consistency error. And you know that means that everything below that branch is just trash. There's no way it could possibly be a valuable solution, so you throw it out. And so if we can throw out more of this tree earlier and higher up, then that's like way better for solving this problem. So our big tree is very sensitive to how wide or narrow it is at the top. So how many choices that very first value has is important, and how many choices that next value has is important, because it means that if we find a consistency error, we can throw away everything underneath it. So if we, instead of just picking the first cell that's unsettled, we pick the first cell that's unsettled that has the smallest number of potential values, we can actually execute this. It's like a 3 to 4 times speed improvement, and it ends up working out pretty well. So to do that doesn't take too much effort. Once we have the indices and the cells, we just sort it. And we have our left value and our right value. And all we want to know is, does the left value have more values than the right value, or does the right value have more values than the left value? It's kind of ugly because of the tuples, but basically this makes sure that the first thing that we check is going to be something that has a very small number of potential options. And if one of those options ends up being incorrect, then we can throw away a bunch of that tree, which is great. So now, that's not right. Write it again. Cool. So you can see now that the board is starting to fill in from the bottom sometimes. It fills in from the middle. It doesn't necessarily always fill in from the top. So that's how we know that our algorithm is working. And it still takes something like 20 seconds to solve. Mostly, oh, there it is. Sweet, there it is. A lot of the iteration time is just from printing. Printing is pretty expensive and slows the algorithm down enough so you can see it. But if you take that out, it's about the same speed up, like 3 to 4 times. It goes from around 30 seconds without printing to like 5 or 6 seconds, which is pretty great. So that's how you solve Sudoku in Swift. There's a few things that I like to highlight at the end. The reason I like this problem so much is that there's a few Swift features that it takes advantage of that I think are basically worth noting. The first one is errors. A lot of people don't like the Swift error system, and it's because a lot of the errors we deal with in iOS programming are asynchronous, and it doesn't really help us there. But when you have a system that is synchronous and has failure modes, it can be really nice to describe those failure modes with something like this consistency error and catch those later and deal with them in special ways as you need to. So there are certain situations where Swift's error handling system is actually quite nice. The second thing I want to call out here is Swift's sequence and collection system is super, super nice. And you can see that in all the little things that we do. We do, like, here we do slicing, we do flat mapping, mapping, filtering, all the fun stuff. And while there's some rougher edges to Swift, it's still a very new language. The sequence and collection handling is really rich and lets you solve these problems. If you can boil down your thing into a sequence or a collection, then you get all these interesting and useful tools that you can use to solve the problem more easily. And if you were at Playgrounds in Melbourne, or if you were in Try Swift Tokyo, you saw my talk about sequence and collection, and you know how much I love that system in Swift. So that's the second thing that I wanted to highlight that this example does a really good job of showing. And the last one is Swift's struct system and the way that it copies values into new references. It ends up being super convenient for this solution to be able to copy that really, really easily. If you want to do this in Objective-C, you got to implement copy with zone, and you got to make a new one, and you got to alloc with zone, and copy the values in the right thing, and then return it. And it's just way nicer to just write var copy equals board. And so, yeah, those are some of the features of Swift that I wanted to highlight with this solution. I hope that it made sense. And if you have questions, I'll be out there after. My name is Soroush, and that's how you solve Sudoku in Swift. Cool.